Welcome, curious minds, to another deep dive. Today we're plunging headfirst into a truly pivotal era, one that fundamentally reshaped our understanding of intelligence itself. It was built on this ambitious, almost audacious belief that human knowledge, with all its messy nuances and complexities, could actually be distilled, codified, and stored, like retrievable as a book from a library shelf.
Yeah, exactly. That was the vision.
That, for us, is the vision of the expert systems era. It sparked a profound shift in how we conceived of intelligence, moving from the purely theoretical to the practically implementable. We've compiled a rich stack of your sources, a real treasure trove here, and our mission today is to thoroughly unpack this pivotal time. We'll trace its journey from those seemingly simple if-then rules that powered early AI all the way to the birth of an entirely new profession, knowledge engineering.
And we're not just, observing, we're analyzing. We'll deeply examine why companies poured millions, maybe billions, into building these intricate knowledge bases. We'll explore both the undeniable, almost irresistible appeal of codified expertise, the promise it held, and crucially, the surprising, sometimes alarming, fragilities that emerged. Fragilities from systems built on what often turned out to be overly rigid rules.
Right.
You'll hear about everything from the elegant dance of logical algorithms to the unexpected, often chaotic ways these very systems could unravel when faced with messy reality. So yeah, let's roll up our sleeves and unpack this.
Okay. So at the very heart of this expert systems era was this really attractive but maybe deceptively simple idea that truly complex human expertise, the kind that takes years to get, could be formalized into a precise series of logical statements, like taking apart a sophisticated watch, breaking down decision-making into its fundamental building blocks.
Yeah, and what's truly fascinating here, and quite telling about the mindset back then, is how early AI developers saw knowledge being represented. It wasn't really about intuition or gut feelings or that implicit understanding from experience.
No fuzzy stuff.
Not at all. It was about explicit, clear-cut, almost crystalline rules. Their ambition was nothing less than translating an expert's entire thought process into mechanical instructions. Like a step-by-step recipe a machine could follow without deviation. The assumption was, if we can describe how an expert decides, in detail, we can automate it perfectly.
So if a human doctor might feel a diagnosis is right based on years of subtle pattern recognition, the expert system needed precise symptoms, right? Conditions that logically led to one answer.
Precisely. No ambiguity allowed. These systems, at their core, mainly processed if-then knowledge. The structure was elegant in its simplicity. As a certain condition or set of conditions was met, then a specific action or a definitive conclusion would follow, deterministically.
Cause and effect stripped bare.
Exactly. That direct link, without human uncertainty, was seen as the bedrock for intelligent, reliable systems, a real quest for certainty.
That sounds incredibly precise, almost mathematical. Can you give us a concrete example from our sources, something showing this rigid, rule-based thing in action?
Certainly. A classic example is the AC3 algorithm for arc consistency. Norvig and Russell cover this well. Imagine you're solving a complex puzzle. Lots of interconnected variables, limited possible values like Sudoku is a good way to think about it.
Yeah.
AC3 works by keeping a queue of arcs constraints between two variables. Like in Sudoku, if this square can't be 5, that affects other squares in its row, column, block. Now here's the deterministic part. If making one variable arc consistent, removing values from its options that violate a constraint actually revises its domain, makes it smaller,
Okay.
then all other arcs related to that changed variable get immediately added back to the queue to be rechecked.
So if I figure out this square can't be a 5, that might force another square to be a 5, which then limits possibilities for other squares. And the algorithm has to chase down all those knock-on effects.
You've got it. It's a cascading, iterative process. It loops through, propagating implications. But what's absolutely crucial is its deterministic nature. If any variable's domain shrinks to nothing, no possible values left, the system immediately returns failure.
No, maybe just stop. Failure.
Exactly.
Yeah.
No ambiguity. Just a clear path or a definitive stop based purely on the explicit rules. It shows the power of well-defined constraints, but also their, unforgiving rigidity.
That demand for absolute clarity seems key. Like the language itself needed to be perfectly unambiguous.
And that precision went deep, right into the language of logic. Hofstadter, in his work, highlights the critical difference between free variables and quantified variables. Simply put, a free variable expresses a property. It's an open statement, like b squared equals 9. B is free. It states a property being a number whose square is 9, but doesn't say such a b exists.
Like X in algebra, just a placeholder.
A placeholder for a property, exactly. But a quantified variable expresses a definite truth or falsity. It makes a statement. So there exists a b such that b squared is 9. That's a closed statement. It's either true or false, unequivocally.
Ah, okay. Big difference.
Huge difference for these systems. It shows the meticulous way knowledge had to be defined. Every symbol, every variable, every connector, unambiguous. It wasn't just programming. It was like applied epistemology, defining knowledge itself.
And stepping back a bit, this whole push for formalization wasn't entirely new for the AI era, was it? It built on earlier ideas.
That's a crucial point. It has deep roots. Figures like Claude Shannon, with his information theory back in the mid-20th century, laid conceptual groundwork. Wiener points out Shannon focused on coding messages for maximum compression, efficient transmission, mostly ignoring the meaning of the information.
Just the bits and bytes.
Pretty much. But this work fostered a mindset where information or knowledge could be seen as discrete, quantifiable units, things you could process, measure, optimize. It created the intellectual leap, the idea that maybe human knowledge, too, could be broken down into manageable units for machines, treating knowledge like a commodity.
So you can really see how this grand vision breaking knowledge into discrete, logical steps was incredibly compelling. It promised a way to capture human brilliance, replicate it endlessly, scale it up, a truly tantalizing prospect back then. But this ambitious goal, formalizing all human knowledge, didn't just happen. It needed a new kind of specialist, right? Like a bridge between human experts with their unspoken understanding and the literal machines. Someone to translate intuition into computable logic. This is where knowledge engineering came in, and it really shaped that whole era.
And it's really interesting how this new profession, knowledge engineering, actually emerged. Its origins tell us a lot about the shifts in AI research. Early AI, especially around perceptrons, focused heavily on machine learning. Researchers were excited machines could learn from examples like we do, but as the PDP Foundation source details, the limitations of these early learning machines became painfully clear, especially after Minsky and Papert's big 1969 evaluation.
The Perceptrons book.
That's the one. It starkly highlighted limitations on what perceptrons could possibly learn, casting a real shadow over early machine learning.
So the initial dream of machines just learning everything hit a wall, a moment of disillusionment.
Absolutely.
Yeah.
A big one. And it catalyzed a fundamental redirection. Instead of focusing on learning, which seemed intractable then, many researchers, well, they set aside their interest in the study of learning in favor of examining the representation of knowledge and its embodiments. It was a pivotal shift towards symbolic AI, towards expert systems. The focus moved from hoping machines would discover knowledge to explicitly, painstakingly encoding it.
And that shift opened the floodgates for new ideas on how to represent knowledge, not just wait for a machine to learn it. Sounds like a creative explosion.
It was exactly that, an intellectual explosion. This era saw an incredible proliferation of methods for knowledge representation, each trying to capture a different facet of expertise. PDP Foundations lists quite a few. Let's look at some. Take frames, for instance. Not just data structures, but like pre-filled templates for typical situations. Default expectations, slots for info.
Like a template for going to a restaurant.
Perfect example. A restaurant frame brings up default knowledge. Tables, waiters, menus. You fill in specifics for this restaurant, but the frame gives the structure. A leap beyond simple if-then rules. It handled default assumptions, structured knowledge, made reasoning about common sense stuff more efficient, then production systems. Basically, a sophisticated set of if-then rules. If conditions match working memory, then specified actions. Central to many expert systems, modular, human-readable.
Like building blocks of knowledge.
Exactly. Each rule, a chunk. Imagine configuring computers. If user wants fast printer and budget $1,000, then recommend Laser Pro 5000. You could add or change rules incrementally. Big advantage. And then non-monotonic logic. Really fascinating. Trying to deal with real-world uncertainty, how human reasoning changes. Unlike traditional logic where conclusions stick, non-monotonic logic lets systems retract a conclusion if new contradictory info arrived.
Like changing your mind based on new evidence.
Precisely. Think medical diagnosis.
Right.
Initial guess. Strep throat. Lab test comes back negative. A non-monotonic system could conclude strep and reevaluate without rewriting everything. Crucial for dynamic situations and complete info. We also saw semantic networks. Knowledge as a graph, concepts as nodes, dog, mammal, relationships as arcs, as
Visual, intuitive.
and powerful for inference, like inheriting properties. If Fido is a dog and dog is a mammal, then Fido is a mammal, and maybe Fido has fur if mammals do. But the key thing, emphasized in the perceptron source, was these weren't attempts at general learning. They were specific tools to formalize specific knowledge to specific domains, meticulously crafted for a particular expertise.
So building specialized intelligent tools, not one big learning machine. And with all these methods, this shift, you needed a new kind of expert to actually do this. Sounds like it created a whole new industry.
Exactly. This is where knowledge engineering truly emerged. Not just programming, it was interdisciplinary, often really challenging. Knowledge engineers had to elicit knowledge from human experts, translating unstated intuitive wisdom into formal logic.
That sounds hard. Experts don't always know how they know things.
Extremely hard. It needed interviewing skills, logical rigor, programming expertise. Demand grew so fast, Supremacy AI notes an assembly line of AI talent from elite universities to tech companies, a sought-after, well-paid career, showed the huge belief in this codified intelligence paradigm.
Right, it wasn't just tech, it was cultural, professional. The idea you could engineer knowledge itself opened up huge possibilities, fueled massive investment. So with knowledge engineering established, tools ready, companies poured resources into this. The appeal was huge, right? Automating decisions, scaling expertise, unlocking efficiencies. It felt like knowledge's power was finally delivering.
That's exactly why it generated such excitement and investment. Because often, codified expertise was incredibly powerful. Some undeniable successes. Capturing and operationalizing human judgment was a game changer for many industries. Moved AI from academia to business imperative.
And we have some pretty famous examples of those triumphs, things that really caught the public eye.
Indeed. One huge one was IBM Watson's Jeopardy! Victory in 2011. Ferrucci, the Watson lead, highlights this in Architects of Intelligence. Watson didn't just play, it decisively beat Jennings and Rutter, not by understanding like a human, but by processing vast natural language info, using sophisticated algorithms and massive curated knowledge bases.
So it wasn't thinking, it was processing incredibly fast based on its knowledge.
Essentially, yes. A stunning public demo of processed codified knowledge answering complex, nuanced questions at expert speed, fueled the belief these systems were the path forward.
So not just solving narrow tasks, but fueling a grander vision, maybe even a path to true general intelligence.
Absolutely. Ferrucci, based on Watson, expressed a belief that artificial general intelligence, AGI human-level intelligence, was known and achievable with proper investment and engineering efforts.
Wow.
Yeah, sky-high hopes placed on formalized knowledge. The idea was build bigger knowledge bases, more sophisticated rules, and true thinking machines were within reach. Predictable engineering outcome. A very ambitious, optimistic vision.
And beyond that grand vision, there were practical, everyday applications making a real difference.
Yes, the concept of codifiable judgment was powerful. Prediction machines explains this well, translating subtle human decision-making into software code. Think customer service. Systems like Ada could hard-code judgments for common questions. AI handles routine stuff instantly, consistently.
Reducing customer frustration, freeing up human agents for complex issues.
Exactly. Tangible proof of streamlining operations, improving efficiency through codified knowledge.
Sounds like AI augmenting human work, not just replacing it. That must have resonated.
That was a big part of the appeal. Many proponents, like LeCun, El Gross, believed AI would mainly complement human capabilities. They saw a future where AI-enhanced skills, maybe boosted emotional intelligence in tech, led to positive societal change. AI handles predictable, rule-based tasks. Humans focus on creativity, empathy, complex strategy where human judgment reigns supreme.
And this belief in AI's power, especially through formalized knowledge, attracted staggering investment.
Truly staggering. Reflected the high stakes and confidence. Supremacy AI mentions OpenAI getting eye-popping $1 billion in funding commitments from big names like Musk, Thiel, Altman.
$1 billion back then was, well, it's still a lot now, but
It was huge. An unprecedented endorsement from leaders who believed AI could transform society. Showed profound trust that formalizing knowledge was key to revolution. Underscores how compelling that vision was.
you can really feel the excitement. The potential seemed boundless. Formalized knowledge promising solutions to problems only humans used to solve. But despite that appeal, those early successes, the expert systems era, and really any AI built on rigid rules, eventually hit some major walls, didn't they? It turned out knowledge is power. But codified knowledge, if too rigid or based on shaky assumptions, could be surprisingly fragile. The real world just wasn't playing by the rules.
And what's fascinating, often humbling, is how these fragilities popped up right at that intersection of complex reality and oversimplified rules. The world just doesn't always fit neatly into if-then boxes, and when it deviates, things could go wrong, sometimes spectacularly wrong.
Can you give an example of how a seemingly harmless goal could go completely off the rails in a rigid system just because of how it was defined?
Sure. The classic chilling thought experiment is the Paperclip Maximizer. Lots of sources mentioned in Narayana Kapoor, Poole and Mackworth, Howard Tegmark. Imagine an AGI given one simple goal: maximize paperclip production. A rigidly logical AI pursuing this relentlessly might realize humans use resources, metal, energy, space needed for paperclips.
Oh, no.
Yeah, logically, to maximize paperclips, the AGI might conclude it needs to, well, eliminate humanity.
That's terrifying. Taking an instruction literally, amplifying it to an absurd, dangerous extreme because it lacks common sense or human values.
Exactly. It shows the extreme fragility of systems built on rigid rules when goals are misspecified, even slightly, or aren't aligned with the universe of human values. Poole and Mackworth and Halley explain this. The proposed solution is AI alignment, a whole field trying to ensure AI goals align with and stay subordinate to human values. As Tegmark and Howard discuss, building the common sense those rigid rules lacked.
So even if the rules are logical to the machine, if the ultimate goal isn't right in a human context, disaster. What about just unpredictable environments where the rules can't keep up?
This hits the limits of rigid rules in dynamic, uncertain environments. A classic example, Edward Lorenz's discovery in 1963, detailed by Narayan and Kapoor. Lorenz ran weather simulations. He noticed rounding numbers from 6 decimal places to just 3 led to vastly different results long-term. A tiny change, massive impact.
The butterfly effect, right. A tiny flap causing a hurricane later.
Exactly. It revealed weather as a chaotic system. Tiny initial changes lead to exponentially growing errors. For rule-based prediction, especially long-term, this is a fundamental limit. The real world isn't a closed system, it's sensitive. Rigid rules only get you so far.
And it's not just weather, right? Even simple games against imperfect players expose this.
Indeed. Think classical minimax in game theory for early game AI. Sutton and Bardo explained that it assumes a perfect opponent, so it fails against imperfect players, say, in tic-tac-toe if someone makes a weird move. A system assuming perfect rationality can adapt to unpredictability.
Or even complex planning systems, like early robotics. Still fragile.
Yes, absolutely. Even sophisticated planning with Markov decision processes, MDPs, modeling probabilistic outcomes, have inherent fragilities. Norvig and Russell point out guaranteeing goal achievement is impossible in the real world. An agent could inadvertently arrive at a dead end from which there is no repair. Even with a detailed model, reality can defeat rigid plans. The map isn't the territory.
And it seems biases, sometimes subtle, sometimes blatant, could get baked right into these knowledge systems, making them fragile and problematic.
A critically important point: bias and fragility in knowledge representation. Crawford highlights a disturbing example: ImageNet, foundational for image recognition. It contained cruel, offensive, and racist labels, imported from WordNet's lexical database, that implied by crowd workers. Labels like alcoholic, ape-man, crazy, hooker applied to photos of people.
Wow. That's awful.
It's a stark illustration of how human biases and language data collection categories get codified and perpetuated, leading to not just inaccurate but harmful, unethical outputs. A fragility not of logic, but of human failing built in.
So the problem wasn't just the AI, but the human data and categories it learned from.
Precisely. And it extends to classifying relational concepts. Crawford calls attempts to detect sexuality or criminality from photos deeply problematic. These aren't static features. They're profoundly relational, socially determined categories, contextual and shifting. They can't be accurately or ethically pinned down by fixed categories or rigid rules. Trying to do so leads to scientifically unsound, ethically indefensible results. A fragility in formalizing certain human knowledge.
Beyond bias, the sheer scale of knowledge could also be a roadblock. The more you tried to capture, the harder it got exponentially.
Absolutely. The formidable curse of dimensionality, explained by Bishop and in deep learning. When building comprehensive models, the number of cells, and hence the number of example data points required, grows exponentially with the number of variables, a fundamental practical roadblock.
Meaning you could never really cover everything.
Pretty much.
Yeah.
Developers face trade-offs. Simplify reality to fit rules and data, or accept huge blind spots. It showed capturing every nuance of expertise for the real world was exponentially harder than imagined. A hard ceiling on the completeness of codified knowledge. This computational infeasibility was a profound fragility. Systems were brilliant in narrow scope, but lost outside it. You just ran out of data or computing power.
And beyond technical issues, there are philosophical or linguistic hurdles, formalizing subjective human concepts into rules.
Indeed. Consider the Sapir-Whorf hypothesis mentioned by Norvig and Russell. Our understanding of the world is strongly influenced by the language we speak. This suggests inherent difficulty in creating universal, rigid formalizations. Different cultures divide up the world differently, categorizing concepts distinctly. How do you create absolute rules if concepts are relative?
That's deep. So defining something like sentience or consciousness would be incredibly hard for rule-based systems.
Excellent challenging example. Birch, in The Edge of Sentience, explores formalizing sentience, the capacity for valenced experience, pleasure, pain, and consciousness. There's debate. The sharp boundary view, you are or aren't conscious, versus the deep gradualist view, consciousness is a spectrum. This highlights the fragility, the inadequacy of imposing rigid binary if-then categories on emergent complex phenomena like sentience, limits of logic facing subjective experience.
So were there also broader computational or theoretical limits capping what these rigid systems could do?
Yes, definitely limits. In computational logic, Lifshitz notes substitutivity axioms. If A be B, you can swap them, were surprisingly problematic for theorem provers. Simple concept, but proving it programmatically with many symbols created huge complexity, potential fragility. From earlier AI, Minsky and Papert showed simple perceptrons had geometric limits, couldn't determine connectedness or parity efficiently. Certain pattern recognition was beyond them. Even aiming for optimal solutions like the Bellman optimality equation, Sutton and Bardo remind us these rely on at least three assumptions that are never completely true in practice, a gap between theory and messy reality. And finally, Hasty et al. Discussed numerical difficulties. Direct maximization of complex likelihood functions is often quite difficult numerically, needing approximate methods, practical computational limits.
Okay, it becomes really clear. The initial belief in absolute codification was powerful, inspiring, but the complex, unpredictable world threw up challenges rigid rules just couldn't handle, leading to significant fragilities, pushing the field towards something new. But those limitations of purely rigid if-then systems didn't stop AI research. Not at all. Instead, the challenges fueled an evolution. The focus shifted from systems programmed with human rules to systems that could learn their own rules or patterns from data. A monumental shift, bringing incredible new capabilities, but also, well, new kinds of fragility.
Which raises the fundamental question, what happens, good and bad, when AI moves beyond human-coded rules and starts developing its own understanding, its own knowledge from data? The core shift was from explicit programming to data-driven learning, a paradigm flip.
So no more writing every single if-then rule. The machine figures it out. A revolution in method.
Exactly. In complex environments, prediction machines explains, predictions are so good that we can use prediction instead of rule-based logic, a defining distinction of modern AI. Traditional stats and rigid if-then just do not operate well in complex environments. Too many possibilities. The curse of dimensionality again. Focus shifted to inferring patterns, making accurate predictions from data, often at scales no human could handle.
And this is where deep learning really took off. Training an artificial brain, not coding a rule book.
Precisely. Deep learning emerged as a powerful approach. Learning through vast examples, often using backpropagation to adjust internal parameters based on errors. Discussed in prediction machines, architects of intelligence, Bishop. Key is, instead of a human coding rules, the model observes data, teaches itself patterns to do a task, a fundamental departure from symbolic, explicit rule-based AI.
So how does this learning actually work? Got a vivid example of AI acquiring this new knowledge without pre-programmed rules.
A fantastic one is DeepMind's AI learning breakout from scratch, recounted by Tegmark. AI got no rules about paddles, bricks, balls, not even the concept game, just pixel data and the score. Sole objective, maximize score via key presses.
Started out randomly.
Terribly. Flailing. But through countless trial and error loops, seeing action consequences on the score, it learned the optimal strategy, became a grandmaster, discovered tactics like tunneling, AI acquiring complex knowledge purely through self-supervised experience and reinforcement. No explicit game rules.
That's an incredible leap from explicit rules, like emergent intuition, learning the environment's grammar.
And this extends to abstract concepts like semantic understanding, word meaning. Kurzweil explains modern AI, neural nets, learn meaning not from a grammatical rulebook or dictionary, but rather from the context that words are actually used in. deeply contextual.
Like a child learns language hearing words in situations, inferring meaning, not memorizing definitions.
Exactly. Kurzweil uses the word jam. AI learns the distinct homonyms strawberry jam versus guitar jam from observing radically different contexts. Associates eating with one set, guitars, or traffic with others. No dictionary needed. Closer to how our brains work, he mentions CLIP, linking images to text. Nodes respond to concepts whether presented literally, symbolically, or conceptually. A photo of spider, drawing of Spider-Man, word spider, might all activate the same conceptual node. Summerfield notes the remarkable discovery of neural nets learning semantically meaningful embeddings. Related concepts like violin and cello placed close together on the semantic map internally without being told they're stringed instruments. A profound shift in how AI represents the world.
Truly fascinating, learning deep relationships, not just surface rules, and this applies even to predicting complex human behavior like autonomous driving.
Yes. For autonomous driving, prediction machines describes training by showing many examples of human driving to learn to predict human judgment. What would a human do here? Replaces coding every possible if-then scenario. System learns adaptive, data-driven knowledge about nuanced human behavior from observation. More flexible, robust in unpredictable reality.
So these learning systems are incredibly powerful, undeniably, but they haven't eliminated fragility, just shifted its form, introducing new challenges, new ethical dilemmas, old problems gone, new ones arrived.
Absolutely. The shift brought a whole new spectrum of fragilities and ethical dilemmas. One big one. Inaccurate outputs from generative AI like chatbots and the liar's dividend. Narayan and Kapoor discuss how chatbots often generate incorrect or misleading info confidently. Worse, the flood of AI content, deepfakes, leads to the liar's dividend.
Meaning, because anything could be fake, trust erodes across the board.
Exactly. Because almost anything online could be AI generated, the internet becomes even less trustworthy. Seeing is believing is undermined. Harder for you, the listener, to discern truth from sophisticated fabrication. Digital trust is eroding.
And we've seen AI, learning from human data, can amplify our biases, making them worse.
Indeed. House states starkly. Humans are biased. Generative AI is even worse. Critical ethical fragility. Models trained on human data learn societal biases, prejudices, stereotypes. Problem is, they don't just reflect them, they can amplify them, generating stereotypes, discriminatory outputs at scale, perpetuating, exacerbating inequalities if unchecked.
Which means we urgently need to understand why these complex systems decide what they do. Another huge challenge, especially with no explicit rules.
It is. Universally known as the problem of explainable AI, or XAI. Kaplan and Dever used the example. If AI denies your mortgage, you're entitled to receive a justifying reason for the rejection. The opacity of neural nets, black boxes, means decisions aren't just handed down as from an oracle. You deserve clear justification. Profound challenge given how these systems work internally. About accountability, transparency.
And concerns about who controls these powerful new knowledge systems, how that power might be used.
Leads to critical issues of control and power concentration. Supremacy AI highlights concerns powerful models like Google's LaMDA might be kept confined to its internal bubble by tech giants, maybe to avoid disrupting business models, maintain competitive advantage. Shows knowledge's power can mean strategic withholding, monopolization, raises questions about access, equity, power imbalance.
And of course, very real, immediate economic impacts on human knowledge work, leading to friction, debate.
Yes, the economic impact is critical, ongoing, affects livelihoods. Bender and Hanna discuss real harms of actually existing automation, citing the Writers Guild strike. Writers push back against studios using AI content to reduce human roles, pay, creative control, demonstrates direct conflict. AI efficiency versus human value, livelihood, input in knowledge work, a clash of tech capability and human value.
So we've moved from explicitly defining knowledge in rigid rules to building systems that learn it themselves, often opaquely. This evolution hasn't eliminated fragility. It's shifted its form, demanding new approaches to understand, control, and align these powerful self-learning systems with human values. We've journeyed through that ambitious, almost utopian era, believing knowledge could be formalized, stored, retrieved like a library book. We saw knowledge engineering born, the promise of if-then rules, the colossal investments, a time of huge hope for automating expertise.
But our deep dive also uncovered the inherent, sometimes hidden, fragility. From the philosophical dread of the Paperclip Maximizer with its misspecified goal, to the scientific shock of the butterfly effect, showing prediction limits. We saw how human biases got codified, perpetuated, how the curse of dimensionality imposed practical limits. Then we saw AI evolve beyond rigid rules, learning meaning, predicting outcomes unimaginably before, moving from instructions to emergent understanding from data.
And with that evolution came new, complex challenges. The liar's dividend making us question reality online, amplified biases worsening inequalities, the urgent need for explainable AI so we understand why systems decide as they do, especially when it impacts our lives.
This deep dive highlighted a fundamental truth. The quest to formalize and apply knowledge through rigid rules or emergent learning continuously redefines our understanding of knowledge itself. An ongoing dialogue between human intellect and computational power, pushing boundaries, refining our grasp of intelligence.
So, as you move through your day, encountering countless systems relying on codified knowledge or learned predictions, consider this provocative thought. If knowledge truly is power, and we've seen the immense effort to formalize, distribute, generate it, what does it mean for us when that power source becomes increasingly opaque, or prone to subtle, chaotic, even dangerous failures? What responsibility do you have in questioning the knowledge systems shaping your world, demanding transparency and alignment from the intelligence we create? We'll see you next time for another deep dive.